Okay, thank you very much. Yes, prior to Ofgem, I spent a number of years working with National Grid, the transmission company in the UK, also in system operations. So I have a perspective from the industry and also from regulator and from government as well. Just to sort of follow on from what Marcus was saying, with system operation being at the heart of the industry, I'd also sort of add, I think it's one of the most exciting areas of the industry where you see all of the different aspects, they all come together in system operation, and it's one of the more challenging areas that has to change. You know, and I congratulate the organisers for focusing on this issue as part of this event, because change in system operation is a key enabler to enabling renewables and enabling sort of industry change in a successful way. As this sort of diagram shows, it's got a picture of an offshore wind farm, which is, if this had happened 10 years ago, the UK had very few, if any, offshore wind farms, whereas now they're probably the fastest growing source of generation that now exists. And the industry, in quite a short period, has just transformed from traditional generation to renewables being the focus, and a whole new industry has generated on the back of that. And what I'd like to do is to sort of share some thoughts about what the current UK system looks like, to give you an example, and what the challenges have been, and what's likely to happen in the future. We've learned an awful lot from experience over the last few years. Some things have gone very well, some things have not gone so well. So what I'd like to do is to sort of share some of that experience with you today. The impact of renewables has been quite profound on system operation, and I'll focus on some of the key issues about that. So if I can just give you a quick overview of the UK electricity system. And apologies, you can't sort of see any detail on the diagram, but I'll explain the sort of main features. So we have currently a peak demand of about 60 gigawatts. So by your standards, this is very small, but it's an island system. It's not synchronously connected to the continent. There are links with the continent of Europe, but they're DC links which are provided at the moment. We've got a number of network companies, completely competitive supply markets and wholesale markets that are in place, and a single system operator. That system operator has recently, it was part of National Grid, it's recently been legally separated to give a greater degree of independence in the actions of the system operator, because the decisions that it makes are absolutely critical to both the networks, generators and suppliers in operating the power system. There's a structure of licenses and codes that govern the rules that people operate in markets, in how they connect to the system and so on. And that's gone through a process of self-governance, where essentially industry parties put forward changes to those codes, changes to the rules. And this is an area that is quite complex. There's about sort of 10,000 pages of codes that individual companies have to sort of understand to be able to compete in this market. So it is very complex and quite slow to change. So one of the challenges is how does that change? Coming back to the physical characteristics that we've got here, there's about 40 gigawatts of renewable generation, a mix between solar and wind. There's 13 gigawatts of solar. That's all appeared in the last 5 years. So it really has been installed very quickly, largely at a distribution level, supported by government subsidies. Wind, which is sort of split half onshore, half offshore, At the moment, there's not any more onshore being built, and it's mostly offshore that is now sort of taking place. What we're seeing is rapid growth in renewables and a decline in the thermal plant. There's expected to be no coal plant running within the next 5 years. There is very little coal operation. There's only 4 coal plants that are now left from a system that was dominated by coal in the past. So the remainder of the thermal plant is gas turbines, and those are expected to reduce over time as well. CCUS, that's carbon capture and storage. At the moment, there isn't any, but there are plans for doing that, and essentially that will use gas turbines but remove the CO2 and store it in reservoirs under the North Sea. The power flows have been changing. I was quite taken by the diagram of India showing the difference in power flows. While it's on a different scale, the UK is similar. Generally, the wind farms are all in the north of the country, the solar farms are in the south of the country. And what we're seeing is exports taking place when the sun is shining or the wind is blowing, and then the opposite way round when those resources aren't available. Generally, the demand centres are all in the south, and the demand isn't changing very much. If anything, it's declining slightly, but the generation mix has been transformed over the last 10 years. Going forward, what we're expecting is many carbon-free days of operation by 2025, and that's what the system is planning for. There are parts of the country, Scotland for example, where there is no carbon generation for large periods of time. So the system operator is getting used to operating a system that areas of it don't have any thermal generation at all, and that's going to increase over time. Just looking forward, this is a sort of a set of scenarios that are produced by the system operator looking forward to 2030 and 2050. And the box at the top corner shows the different scenarios. The two on the left are really different versions of business as usual, gradual growth in renewables, but a lot of thermal generation. The other two show a huge growth in renewables. The top one has the renewables largely at a distribution level. The bottom one has renewables at a transmission level. And all of these pictures, to varying degrees, sort of tell the same story. There's a greater growth in interconnectors. Carbon capture and storage is expected to increase over time, basically to provide flexibility. There will be some more nuclear. Thermal is still expected to be around even by 2050, providing particularly flexibility services. Solar and wind and other renewables, which are biomass primarily, are all expected to increase over that period of time. The demand does change, largely due to the impact of electric vehicles and heat that may convert from gas to electric. The one thing that this is, you can say about this is that it will be wrong. As with all scenarios, it's almost impossible to predict what the future will be, but it gives a picture that the system operator is planning for all of these scenarios, that it's got the right tools, the right processes to cope with all of that. And more recently, this diagram was produced before the net zero target was produced, where there will be even more dramatic changes that are needed to the generation mix. So, for example, there will be no thermal plant without CCS, and there may be growth in other areas. So that's the future profile that the system operator and the industry, and indeed government and regulators, are looking at going forward. So we've coped with change to date, and these are the changes that are expected ahead. So some of the impacts on system operation, what has the operator had to deal with? This sort of just gives a couple of examples. The chart on the left shows the growth in solar energy on the distribution networks. Now, this has grown from nothing to about 13 gigawatts of capacity, and this sort of shows the actual energy produced over the period of time. And as you can see, there's a profile where it increases during the summer and drops off during the winter. Now, that's driven by subsidies. Those subsidies have recently stopped. So until solar power becomes cheaper, panels become cheaper, that profile is likely to stay sort of pretty flat, may only increase slightly. But as soon as solar panels start to become economic, we can expect to see that profile increase again. So these things are driven by government policy. The system operator doesn't know where this solar is. The comments about metering were made earlier on. It's not clear where the solar panels are installed. The meters aren't necessarily accurate. They may not be installed. So trying to predict what the solar generation will be is again a challenge, and tools have had to be developed to allow that to be closely modeled. The right-hand chart again shows some of the challenges that the system operator has from managing the balance of generation and demand. We're actually seeing demands, if you look at the blue area, being at a minimum during the afternoon when the distribution networks are exporting solar power, thereby reducing the transmission connected demand, which means that the type of transmission constraints and modes of operation have had to change to cope with that. This diagram has already been shown once. This was an example of a failure, a blackout, which doesn't happen very often in the UK. This is the first one for 10 years. And there was a lightning strike followed by essentially 3 events that happened after that. Firstly, there was a wind farm that tripped for unknown why it tripped at that time, at the moment. The frequency fell, and then as the frequency fell, about 500 megawatts of distribution generation tripped as well. Then this was followed by a loss of a gas turbine that tripped altogether, exceeding the normal amount of reserve that the system operator is required to carry on the system. Then there was a demand reduction to recover the frequency, and automatic demand reduction, and there was then another generator failure of another 200 megawatts or so. So this raises a number of questions. Was there sufficient reserve? Because reserve costs money, and there's a risk and return question around that. Perhaps more importantly, was there sufficient inertia on the system so that all the remaining generators were able to recover over that period of time? And I think this is the first time I've seen inertia in the sort of headlines of some of the national newspapers, recognizing this as a potential issue. But also importantly, did the distributed generation operate as it should have done? Were the protection settings right at that point in time? So it raises a whole set of questions, all driven by the fact that in today's society, it's sort of unacceptable to have any power loss. It grabs the headlines and is much more relevant to society than perhaps it was in the past. So I think you can sort of look at this, and there were the headlines, should we blame renewables? But there's a lot of other factors about this type of system operation, which I'm sure will lead to some learnings going forward. But these are, at the end of the day, people that were cut off for about 40 minutes at most. There was some transport disruption, but again, it's a question for society. Is that the type of event that we should be dealing with? So on to lessons learned, and I'll deal with the sort of technical ones first. System inertia, as we're getting less synchronous generation, and while some of the wind farms and solar panels can start to provide types of inertia and types of response, it's not the same as the traditional thermal plant. So frequency response, how is that managed, is a key issue, and new measures have to be put in place. It is possible to manage it, but it's not possible to use the same tools that we had in the past. Things like rate of change of frequency can affect distributed generation, and has that really been thought about in the same way? The amounts of reserve, reactive power, and black start all need to be thought about in a decentralized energy environment where you don't have the same amount of centrally connected generation. These are not new issues, but I think they are greater priority now than they have been in the past. So any power system engineer would look at these and say, it hasn't changed, these are all the things that we used to look at in the past, but I think they're now much more at the forefront of decision making. The other area is connections, getting grid connections available on time to connect renewables, which is a non-trivial task, and sometimes the capacity may not be there at the site that the renewables are at, and putting the mechanisms in place, and Ofgem has played a key role in this, Ofgem and government, in putting mechanisms in place where sometimes generators can connect ahead of the transmission system being fully available, and the use of non-firm capacity agreements has again allowed renewables to connect faster than the grid can be built to support it. Things like charging arrangements then need to be changed because they're designed for the old world where you've got big generators and now lots of smaller ones with different charges. And the other thing that is changing is consumer engagement. The aspect of the energy sector that's never really discussed is what the demand side is doing, demand response, and the ability of customers to engage in the power market. And what we're seeing more and more, either directly through putting solar panels on their roofs or working through aggregators, is these smaller groups of customers participating directly in the energy market. And it's starting to look a little bit more like a bottom-up market where people are starting to make a choice rather than the top-down design that we've had in the past. I'll just mention this very quickly. Flexibility, we've spoken about that at length. One of the key things in the UK, particularly because we are an island system, is the forecast growth in energy storage that is roughly about 1 gigawatt at the moment, but is expected to grow by many times. And this will largely be batteries sort of needed to provide fast response type services. It's pretty unknown how large this will grow, but there's a huge, I think there's about 18 gigawatts of parties who've made connection applications to put batteries on the system, looking ahead to this market developing. And the thing with batteries is that they can be installed quite quickly. The other big uncertainty is growth in electric vehicles. There's about 40 million vehicles on the roads in the UK at the moment, and about 1% are electric currently. But the government's plans are to phase out internal combustion engines over the next 15 years, which means that there will be a dramatic change in demand and how that impacts on the electricity system. It could be a problem. It could also be a great benefit if vehicle-to-grid storage is used in lieu of separate batteries. But we're at the very early stages of that journey. But it's one issue that system operators are going to have to be well on top of in the future. So our lessons: you can accommodate large amounts of renewables, actually using the old energy system primarily and operating it in a different way. So it is pretty adaptable to growth in renewables. And keeping reliability can be achieved even with large penetrations of renewables. And another positive is the ability of customers to engage and become involved in the energy system. On the negative side, there are certainly concerns about inertia, how that's decreasing, and understanding and measuring that to a much greater degree and mitigating the effects of losses. Storage markets for storage don't really exist. How to incentivize and encourage this type of investment, the whole growth in flexibility markets doesn't really exist yet. And another important area, I mentioned the rules that govern the system, the grid codes, the various charging agreements and so on. A lot of those are very hard to change, and the incumbents often don't want to change them because it protects their business model. So what we're seeing is certainly some challenges in that area. Just looking ahead, and again, I won't go through each of these in detail, but just to give you a flavor of what are the key drivers for change. We're seeing faster technology change in the power sector than we have for decades, I think. Things like electric vehicles, digitization, the use of data, customers sort of taking control of their own energy demand. We're also seeing the speed of change increasing with new policy announcements, the whole ability to set up new business models, new participants in the industry. It's challenging the status quo. We've talked about some of the power system developments, growth in decentralization, inertia, capacity, grid defection. I mean, we're not really seeing it in the UK, but in some countries like Australia, it's becoming a real issue where the grid is just used as insurance, and people will defect from the grid and have their own sort of microgrid and so on. And I've mentioned sort of governance, and the ability to change and change the rules is going to be increasingly important. And my final slide is that when we look to what this means for the different sort of parties in the industry, it means utilities of the future are likely to look very different from the ones of today, more focused on renewables, more focused on customers and how they interact with those customers, perhaps more directly than they have in the past. Customers themselves, how they take the lead in communicating and dealing with their sort of utility tariffs, you know, in the same way that you would use your mobile phone and so on. Big change for policymakers as well, in that they need to enable a lot of this change, and in some cases need to incentivize and encourage it, and of course ensure compliance. And the system operator has to deal with all of this, but again, there are opportunities for the system operator to take advantage of the new digital tools that are available, the new data, the information to be able to manage the power system going forward. So I think across the whole area, it's a very exciting time in system operation, dealing with some of these challenges going forward, which I'm quite sure is achievable in the UK and in here. Thank you.